The universe's fundamental laws begin to fracture at these cosmic frontiers. We are about to venture into 30 extreme environments inside galaxies where known physics breaks down completely. By the end of this journey, you will understand how these cosmic anomalies are forcing scientists to rewrite the textbooks. What happens to matter inside a black hole's singularity? And why do some galaxies seem to float through space with almost no dark matter at all? Which of these cosmic puzzles do you find most compelling to solve? At the very center of our galaxy, a gravitational monster named Sagittarius, a star, contains over 4 million times the mass of our Sun. All that unimaginable weight is crushed into a single point of infinite density, a singularity where the fabric of space and time itself tears apart. The rules of physics as we know them simply stop working here. This is not merely a place of immense gravity. It is a boundary where reality, as we understand it, reaches its ultimate limit. The event horizon acts as a one-way cosmic curtain. Once anything crosses this threshold, it can never send information back to our universe. According to our best theories, an object falling in would be stretched into a stream of atoms by tidal forces in a process scientists call spaghettification. Yet the true fate of that matter remains one of science's greatest enigmas. Does it crash into the solid, infinitely dense core of the singularity, or does it pass through into another realm of existence entirely? Our current laws of physics offer no definitive answer. They simply give us a mathematical error message, a division by zero that signals a complete breakdown of our understanding. This profound mystery at the heart of every large galaxy forces us to confront the limitations of Einstein's theory of general relativity and compels us to search for a deeper theory of quantum gravity that can describe the unknowable. But the violence of a dormant singularity is nothing compared to the fury of one that is actively feeding. Picture a cosmic engine of almost unimaginable power, a single object so brilliant it can outshine the combined light of every star in 1,000 galaxies. This is the heart of a quasar, an active galactic nucleus where a supermassive black hole feasts on a steady diet of gas and stars. Matter spirals inward at nearly the speed of light, forming a superheated accretion disk that glows with the heat of millions of degrees. From this maelstrom, twin jets of pure energy often erupt, shooting subatomic particles across intergalactic space for hundreds of thousands of light years. The efficiency of this process is staggering, converting the mass of falling matter into pure energy with a proficiency that approaches, and may even break, the known theoretical limits for such a system. How can a black hole, an object defined by its ability to trap light, become the universe's most powerful source of it? The answer lies in the chaotic physics just outside the event horizon, where magnetic fields of incomprehensible strength twist and contort the superheated plasma. These fields act like cosmic railguns, funneling and accelerating material into those incredibly thin, focused jets. Yet our best models of magnetohydrodynamics, the science of how magnetic fields interact with fluid matter, fail to fully explain how these jets remain so coherent over such vast distances. They do not dissipate or scatter, but punch through the thin gas between galaxies in a straight line for eons. Observations from space telescopes like Chandra and Hubble show these structures varying in brightness in ways that defy simple explanation, hinting at forces and mechanisms we do not yet comprehend. The existence of these perfect cosmic lasers suggests that our understanding of plasma physics, under the most extreme conditions the universe can conjure, is fundamentally incomplete. To solve this, we may need new physics that can describe how space, time, and energy interact at their absolute limits, a quest that inevitably leads us to another, even more elusive cosmic phantom, dark matter. These stellar cataclysms are the universe's most powerful explosions, events so violent they briefly outshine entire galaxies. In just a few seconds, a single gamma-ray burst can release more energy than our Sun will generate across its entire 10 billion-year lifespan. There are two primary architects of this cosmic chaos. The long-duration bursts signal the death of a truly massive star, its core collapsing directly into a black hole. The short-duration bursts are even more dramatic, born from the final, spiraling embrace of two ultra-dense neutron stars. Both scenarios forge the same terrifyingly efficient engine, a newborn black hole that fires twin jets of matter and radiation at nearly the speed of light. It is within these narrow, focused beams that the extreme physics unfolds, creating a natural laboratory for conditions we could never hope to replicate on Earth. The sheer energies involved here might even allow us our first experimental glimpses into the quantum nature of gravity itself. Scientists use what is called the fireball model to describe the initial explosion and the expanding shock waves. Yet this model cannot fully explain the intricate dance of light we observe, the specific ways the brightness fades, or the strange properties of the lingering afterglow that can shine for days. This tells us our understanding of how matter behaves at these ultimate speeds, in what are called relativistic shocks, is fundamentally incomplete. The data itself presents profound puzzles. The Fermi Gamma-ray Space Telescope has detected individual photons from these bursts with energies so high they defy conventional explanation. For these particles to reach us without being absorbed by the universe's background fog of light suggests that our most basic assumptions about space and time, a principle known as Lorentz invariance, might be breaking down at these extremes. The new era of multi-messenger astronomy, where instruments like LIGO and Virgo feel the ripples in spacetime from a neutron-star merger at the same moment telescopes see the resulting gamma-ray flash, has opened an entirely new window. Yet even with this combined view, the central mystery remains. What cosmic accelerator can possibly hurl particles to such unimaginable energies? To find that answer, we must look to the strange, silent corpses these explosions leave behind. The silent corpses of stellar explosions can harbor a different kind of violence. Deep within a magnetar, a magnetic field of almost incomprehensible strength lies in wait. This force is not merely strong, it is a fundamental property of reality amplified to a destructive crescendo. A magnetar's magnetic field measures 1,000,000 billion times more powerful than Earth's own protective shield. If one were to approach within 1,000 kilometers of this object, the field would effortlessly rip the very atoms of your body apart, tearing electrons from their nuclei from a staggering distance. Here, the rules of quantum electrodynamics, the very theory that describes how light and matter interact, are pushed into a strange and alien regime. The vacuum of space itself ceases to be empty and transparent. Instead, it becomes a kind of crystal, bending light in two different directions depending on its polarization, an effect called vacuum birefringence. This is a direct prediction of quantum theory, yet it is an effect so subtle it only becomes visible in the presence of such a monstrous magnetic field. The field's influence is so absolute that it warps the shape of atoms, squeezing their electron clouds into long, thin cylinders. In this environment, the concept of a normal chemical bond is meaningless, and the properties of matter become something we can scarcely model. The energy stored in these twisted magnetic fields is released in cataclysmic starquakes and flares. In a fraction of a second, A single magnetar flare can release more energy than our Sun has emitted over the last 100,000 years. This is a magnetic reconnection event on a scale that defies our best plasma physics simulations. We observe these objects spinning with a precise rhythm, only to be interrupted by sudden glitches, tiny jumps in their rotation. These glitches are whispers from the magnetar's heart, hinting at a complex interior where nuclear matter exists in a superfluid state or forms exotic crystals, phases of matter that are impossible to recreate in any laboratory on Earth. How can matter behave when magnetic force is the absolute ruler of its existence? The search for answers to this question leads us from these isolated, spinning magnets to the very fabric of the cosmos, to places where gravity itself may be woven from hidden dimensions. Within the silent heart of a neutron star, matter exists in a state of absolute surrender. Picture a single sugar cube possessing the mass of an entire mountain, a density so extreme that atoms themselves are crushed out of existence. Electrons are forced into protons, transforming them into neutrons until the entire star becomes a city-sized atomic nucleus, a perfect, seamless ocean of the most fundamental nuclear material. Yet this is only the beginning of the strangeness. Deep within the core, the pressure may become so unimaginably great that even the neutrons themselves can no longer hold their form. They may shatter, dissolving into a seething soup of their own constituent parts, quarks and gluons. This Quark-Gluon Plasma is a state of matter that has not existed freely since the first microseconds after the Big Bang, a primordial broth where the very rules of the standard model of particle physics are tested to their breaking point. Other theoretical models suggest the formation of hyperons, exotic particles that incorporate strange quarks, creating a form of matter that is profoundly unstable everywhere else in the universe. The true nature of this core, the star's final equation of state, remains one of nuclear physics' most sought-after prizes. The answer dictates the ultimate fate of these stellar corpses, setting the precise mass threshold at which they must inevitably collapse into a black hole. A difference of just one solar mass in this limit changes our understanding of how the universe forges its heaviest elements. We are slowly piecing this puzzle together by listening to the universe itself. The gravitational waves from colliding neutron stars, felt by observatories like LIGO, send ripples through spacetime that carry the unique imprint of how stiff or soft this ultra-dense matter truly is. Each cosmic crash provides another data point, yet the core's precise composition remains shrouded. Further clues come from the stars themselves in their precise spins. A pulsar is a cosmic metronome, its rhythmic flashes of light measured with nanosecond accuracy. Then, without warning, a starquake deep within can cause a pulsar glitch, a sudden, tiny jump in its rotation. This is the signature of a fantastically complex interior, where a superfluid sea of neutrons spins independently from the solid crust of star stuff above it. At times, this fluid locks back onto the crust, transferring energy and giving the entire star a sudden speed boost. Our models of fluid dynamics cannot fully capture the chaotic interplay within this nuclear reactor. Even the minuscule mountains on a neutron star's surface, mere millimeters high, represent a titanic struggle. These tiny imperfections create a strain on the crust that pushes against the absolute theoretical limit of how strong matter can possibly be. What does it mean for material to exist at the very edge of its own destruction? The heart of a neutron star is a laboratory for states of matter we cannot name, governed by principles we have yet to fully write down. Solving this mystery not only reveals the fate of dead stars, but forces us to ask what matter is truly capable of becoming under pressure, a question that leads us to the ghostly presence that holds the cosmos together. This invisible architecture, dark matter, forms a ghostly halo that cradles every galaxy. We see its gravitational signature everywhere, from the way stars whip around a galaxy's outer rim to the way it warps the fabric of space itself, bending the light from more distant objects in a phenomenon called gravitational lensing. Yet after decades of searching, our most sensitive detectors buried deep underground have found nothing. This elusive substance, which makes up about 85% of all matter, refuses to interact with the ordinary atoms that make up our world in any way we can directly measure. The leading candidate for decades has been a theoretical particle called a weakly interacting massive particle, or WIMP. These hypothetical particles would be heavy and slow-moving, only communicating with normal matter through gravity and perhaps the weak nuclear force. But the persistent silence from our detectors has forced physicists to broaden the search. Could dark matter be made of actions, ultralight particles that waft through the cosmos like a quantum mist, or perhaps sterile neutrinos, strange, heavier cousins to the familiar neutrinos that already stream through our bodies? Each idea is compelling, but each also faces its own profound challenges when matched against the universe we observe. The puzzle only deepens when we look at the largest structures in the cosmos. Supercomputer simulations of the universe, running the laws of physics forward from the Big Bang, predict how dark matter should be distributed within galaxy clusters. They consistently show halos with a particular, dense profile at their very centers. Yet when astronomers measure the actual gravitational effects in these inner regions, the observations sometimes tell a different story. The dark matter appears less clumped, its distribution smoother than our best models predict. This is more than a minor discrepancy. It is a fundamental tension between theory and observation. What process is preventing the dark matter from collapsing into the expected cusp? Does it involve some unknown form of interaction between dark matter particles themselves, a hidden force that only governs the invisible majority of the cosmos? Or does this persistent mismatch point toward an even more radical solution, that our understanding of gravity itself, Einstein's theory of general relativity, requires modification on the vast scales of galaxies? This cosmic ghost not only evades capture but challenges the very foundations of physics, leading us to a related enigma that dances at the edge of our vision. Yet this ghostly presence might have just left its first visible signature. At the very heart of our own Milky Way, an unexplained glow of high-energy light pulses with a rhythm that defies all conventional explanation. Observations from the Fermi Gamma-ray Space Telescope have mapped a mysterious excess of gamma rays, the most energetic form of light, concentrated in the galactic core. This is not the uniform background radiation we would expect from known processes. Its specific energy signature and the way it spreads across space do not perfectly match the expected profiles of known objects like pulsars or the interactions of cosmic rays with gas. This persistent, unexplained signal has ignited a fierce debate among astrophysicists, pointing toward something strange happening in the galaxy's most crowded district. One of the most thrilling possibilities is that we are witnessing the final moments of dark matter itself. Theoretically, when two dark matter particles collide, they could annihilate each other in a flash of pure energy, producing the very gamma rays we detect. If this is true, the galactic center excess would be our first indirect glimpse of the universe's dominant form of matter, a discovery that would shatter the foundations of modern physics. Yet the properties required for this annihilation are strangely specific, challenging many of the most popular models for what dark matter could be. The particles would need to be of a particular mass and annihilate at a specific rate, a set of conditions that feels almost too perfect. This has led scientists to vigorously explore other, more conventional cosmic culprits. Could the glow be coming from a vast, unseen population of ancient, rapidly spinning neutron stars known as millisecond pulsars? These faint objects would be incredibly difficult to spot individually but could collectively create a diffuse glow. Alternatively, the signal might be an echo of a past era of furious star formation, a burst of activity that flooded the center with radiation whose remnants we are only now deciphering. However, each of these astrophysical explanations struggles to fully account for the signal's unique characteristics. The plot thickens when we look at the shape of this mysterious emission. The glow is not a perfect sphere centered on the black hole, Sagittarius a star. Instead, its morphology appears slightly elongated, potentially aligning with the galaxy's central bar, a vast structure of stars, or perhaps even with the underlying distribution of the dark matter halo itself. This subtle detail adds a profound layer of complexity, forcing astronomers to build ever more sophisticated models that intertwine the physics of particles with the grand architecture of the galaxy. What underlying process, either a new type of particle or a new class of astronomical object, is capable of generating this persistent, high-energy hum? Unlocking the secret of the galactic center excess may do more than just identify a new light source. It could reveal an entirely new set of physical laws operating in the most extreme environments the galaxy has to offer. A signal flashes into existence for less than a blink of an eye, yet in that millisecond it releases more energy than our sun will for an entire century. These are fast radio bursts, cosmic screams that have traveled across unimaginable voids only to vanish without a trace. Since their chance discovery in 2007, they have presented a puzzle of almost absurd proportions. How can something so brief be so impossibly bright? The answer lies in a concept called coherent emission, where countless particles radiate in perfect, synchronized unison, like a stadium crowd chanting as one. This is fundamentally different from the random, chaotic light of a normal star, and it points toward an engine of extraordinary and focused power. While some of these bursts are one-time cosmic catastrophes, others repeat with complex, unpredictable patterns, suggesting multiple different monsters are at work in the dark. The repeating signals come from sources that are clearly surviving their own immense outbursts, pointing not to a final destruction, but to a recurring, violent process. The environment around these sources adds another layer of mystery. The radio waves from some bursts show extreme Faraday rotation, a twisting of their signal that indicates they have passed through magnetic fields of ferocious strength, far beyond what exists in the typical space between stars. This suggests they originate within dense, magnetized nebulae or in the terrifying vicinity of objects like magnetars. A major breakthrough came with the recent detection of a fast radio burst from inside our own Milky Way, definitively tracing one type back to an active magnetar. Yet this identification solved one mystery only to deepen another. Our standard models of a neutron star's magnetosphere simply cannot explain how such an intense, coherent pulse of radio waves is launched in a mere millisecond. The physics of how plasma behaves in such an absolute magnetic dictatorship remains one of the great unsolved problems. How can a single object generate such a clean, powerful signal across such a wide range of frequencies simultaneously? The solution may require a new understanding of how energy is stored and released in these cosmic magnets, a sudden reconnection of magnetic field lines on a scale we can barely conceive. Each new burst recorded by telescopes around the world is another piece of data in this high-stakes investigation, forcing us to question if we truly understand the most basic ways the universe can shout into the darkness. Floating in the vast intergalactic sea are ghost ships, galaxies as large as our own Milky Way but containing only a tiny fraction of its stars. These are ultra-diffuse galaxies, cosmic mirages so faint they nearly blend into the empty backdrop of space. Their starlight is spread so thin that spotting one is like trying to read a single page of a book from 1,000 kilometers away. This extreme dimness hides a deeper, more fundamental mystery. According to everything we know about how galaxies are built, these fragile structures should not exist at all without the gravitational scaffolding of dark matter to hold them together against the immense tidal forces of their neighbors. Yet when astronomers measure the motions of stars within some of these ghostly giants, they find something astonishing. The stars move far too slowly, suggesting there is little to no dark matter present. This is a direct contradiction to our standard models, which insist that a dark matter halo is the essential seed from which every galaxy grows. How can such a vast, sparse collection of stars survive without this invisible anchor? The very existence of these dark matter-deficient galaxies suggests either a formation history we have never considered or a subtle flaw in our understanding of gravity itself. The plot thickens when we find other ultra-diffuse galaxies that do possess the expected amount of dark matter, making the contrast even more baffling. How can two galaxies, similar in size and stellar content, have such dramatically different hidden architecture? This cosmic divergence points toward environmental factors we are only beginning to map, perhaps histories of violent interactions that stripped one galaxy of its dark matter while leaving the other intact. Or it may be evidence of a more exotic type of dark matter, one that can interact with itself in ways that allow it to be swept clean from certain regions of space. Each of these ghostly galaxies is a natural experiment, testing the fundamental rules we believe govern the birth and life of all cosmic structures. Their silent, transparent forms challenge us to explain why they are even here, pushing our models of galaxy evolution into uncharted territory and forcing us to question if we truly understand the relationship between the visible universe and the invisible force that supposedly dominates it. A perfect circle of brilliant blue stars surrounds a golden core, separated by a dark and seemingly empty void. This is Hoag's object, a galaxy that looks more like a cosmic eye than a typical spiral. Its structure is so pristine and geometrically perfect it challenges our most fundamental ideas about how galaxies form and endure. Standard models tell us such a clean separation between a central bulge and a star-forming ring should not remain stable over billions of years. The gravitational dance of stars should have blurred the sharp edges or drawn bridges of matter across the gap, yet here it is, a cosmic fossil of an impossible form. The most common explanation points to a violent past, a smaller galaxy piercing the heart of a larger disk galaxy like a bullet through a bullseye. This immense collision would have sent a powerful density wave rippling outward, compressing gas and igniting the firestorm of new stars we see as the Blue Ring. But this story of cosmic violence feels incomplete when faced with Hoag's perfect symmetry. The object is profoundly isolated, with no obvious culprit galaxy nearby to have caused such a disruption, and the ring itself is almost perfectly circular, lacking the distortions or tidal tails we would expect from a chaotic encounter. Could the answer lie not in a collision, but in a galaxy's own internal instability? Some theories suggest a central bar of stars, a common feature in spiral galaxies, could have formed and then dissolved, its gravitational influence funneling gas to the outer edges to form the ring. Others propose a slow, steady accretion of intergalactic gas could build such a structure from the outside in. Yet each of these ideas struggles to fully account for the clean, vast emptiness between the ring and the core, a chasm that appears devoid of the stars or gas that should logically connect them. How can this cosmic wheel maintain its perfect shape without flying apart or collapsing inward? The very existence of Hoag's object and the few other ring galaxies we have found suggests there are pathways of galactic evolution we have not yet mapped, processes that can sculpt matter with an artist's precision. Studying these rare gems may reveal subtle laws of galactic dynamics that are lost in the crowded, chaotic swirls of more common spirals, forcing us to reconsider what is possible within the quiet, slow-motion ballet of the cosmos. But what if an entire galaxy existed in perfect darkness? This is the haunting possibility of a dark galaxy, a cosmic structure made almost entirely of dark matter. Imagine a vast, invisible island in space, possessing the mass and gravity of a full-fledged galaxy like our Milky Way, yet containing no brilliant spiral arms, no glowing nebulae, and only a handful of ancient, dim stars. These hypothetical objects represent the ultimate dark matter environment, a place where the invisible force that shapes our universe operates in near-total isolation. Their existence would offer scientists a pristine laboratory, a chance to study dark matter's fundamental properties without the complicating noise of normal matter and its complex physics. We have hints that such phantoms might be real. Astronomers have identified puzzling candidates through their subtle but measurable gravitational effects. Some reveal themselves by warping the light from more distant galaxies, a clear sign of a massive object's presence, even when no galaxy is visible in that location. Others are suspected from anomalies in the rotation curves of visible galaxies, where the motion of gas and stars suggests they are being tugged on by a massive, unseen neighbor. The challenge of confirmation is immense, as these objects emit almost no light for our telescopes to catch. If dark galaxies are confirmed, they would force a major rewrite of our theories of cosmic structure. Our standard models suggest that dark matter halos act as gravitational wells, naturally drawing in ordinary gas that then cools, condenses, and ignites into stars. A dark galaxy presents a profound contradiction to this story. It implies that a massive dark matter halo can exist for billions of years without ever lighting up. Why did star formation fail here? Was the primordial gas somehow prevented from falling in, perhaps pushed away by intense heat or powerful magnetic fields in the early universe? Or did the gas collect but remain too turbulent or too warm to ever collapse into dense, star-forming clouds? Some of the best dark galaxy candidates are not completely black. They show faint, diffuse emission or host a sparse population of old stars. This makes the mystery even deeper. Why did these halos only form a tiny, stunted stellar population, while a halo of similar mass elsewhere gave birth to 100 billion suns? The answer may lie in the subtle physics of dark matter itself. Perhaps certain types of dark matter particles can generate heat or radiation that prevents gas from cooling, effectively sterilizing the galaxy before it can be born. Or maybe the environment around a dark galaxy was simply too quiet, lacking the gravitational nudges from passing galaxies that can trigger star formation in more crowded cosmic neighborhoods. Unlocking the secret of these dark realms would tell us not only about the nature of the invisible majority of matter, but also about the delicate and sometimes thwarted process of galactic birth itself. Rising from the galactic plane like two colossal, invisible lungs, the Fermi Bubbles stretch for 25,000 light-years above and below the Milky Way's core. These are not static structures but the fossilized imprint of a titanic explosion, a burst of energy so immense it flooded the galaxy's halo with hot gas and high-energy particles. The energy required to inflate these vast structures is almost beyond calculation, equivalent to the simultaneous detonation of millions of supernovae. The source of this cataclysm remains one of the galaxy's deepest secrets. Was it a frenzied feeding event from our own supermassive black hole, Sagittarius A star, in the distant past? Or could it have been a period of such intense, concentrated star birth that the combined stellar winds and explosions literally blew a hole in the interstellar medium? Either scenario presents a profound challenge to our models of how galaxies regulate their own growth and evolution, a process astronomers call galactic feedback. The bubbles themselves are not empty voids, they are filled with a thin, magnetized plasma and are glowing faintly in the most extreme forms of light, from gamma rays to microwaves. This emission tells a story of cosmic rays, subatomic particles accelerated to nearly the speed of light, racing through the bubble's interior. Yet the way these particles are distributed does not match our standard theories for how shockwaves from a single explosion should accelerate matter. The edges of the bubbles present another stark contradiction. They are remarkably sharp and well-defined, like the surface of a soap bubble, standing against the diffuse background of intergalactic space. According to our best fluid dynamics models, these boundaries should have blurred and dissipated over millions of years, their heat and particles diffusing into the surrounding emptiness. The fact that they have not suggests that powerful magnetic fields are acting as a containing sheath, or that some form of continuous, low-level energy injection is maintaining their pristine walls. How can such coherent structures maintain their integrity for so long against the relentless pull of entropy? The answer may lie in processes we are only beginning to model, where chaotic turbulence and large-scale magnetic reconnection work together to create unexpected order. These galactic winds are not just a historical curiosity, they are active, dynamic systems that continue to transport energy and metal-enriched gas out of the galaxy, effectively shutting down future star formation in their wake and sculpting the ultimate fate of the cosmic ecosystem they inhabit. Light from the distant universe does not always travel in a straight line. It can be bent and warped by the immense gravity of entire galaxies or clusters acting as cosmic lenses, creating multiple, distorted images of the same background object. This phenomenon, called strong gravitational lensing, is one of our most powerful tools for testing the fabric of the cosmos. Yet these natural telescopes are revealing subtle but persistent flaws in our predictions. The problem appears in the precise brightness of the multiple images. According to our best models of gravity and dark matter, the light arriving along different paths should have specific, calculable ratios. Yet time and again, the observed flux ratios are wrong. One image will be systematically brighter or dimmer than our equations dictate, as if something unseen is subtly altering the light's journey. This is not a minor accounting error. It points to a fundamental gap in our understanding of the lens's structure. The standard model of cold dark matter predicts that the halo of a massive galaxy should be teeming with thousands of smaller, invisible subhalos, the dark matter foundation for satellite galaxies. Yet when we look through these cosmic lenses, the population of visible satellites is far lower, and the gravitational effects of the predicted dark substructure seem to be missing. Where is this invisible crowd? Are the dark matter clumps simply not there, or are they failing to ignite stars and thus remaining completely dark? Some lens systems show the opposite problem, revealing evidence of extra clumping, small-scale concentrations of mass that our smooth halo models do not account for. These could be the fingerprints of those elusive dark matter subhalos, or they might point to unexpected complexities in how dark matter interacts with itself. Perhaps they are even vast, unseen congregations of rogue planets or cold gas, baryonic matter hiding in plain sight. The most profound tension comes from measuring time. When a distant quasar flickers, that flicker appears in each of its lensed images at slightly different times, as the light has traveled different path lengths around the lens. By carefully measuring this delay, we can calculate the universe's expansion rate, a crucial cosmological parameter. Yet these time delay distances sometimes disagree with the values obtained from other methods, like the cosmic microwave background. This is more than a calibration issue. It suggests that our assumptions about how light propagates through the complex cosmic web over billions of years might be incomplete. Why do these natural experiments, which test gravity at its most extreme, consistently present us with the same small, stubborn anomalies? Each distorted image is a question, challenging whether we need a more complex portrait of dark matter or a fundamental revision of gravity itself. Massive rivers of primordial gas flow silently through the galactic halo, moving at speeds that defy the Milky Way's rotation. These high-velocity clouds are not small wisps. They are colossal structures of neutral hydrogen, some stretching for thousands of light years and containing enough raw material to forge millions of new stars. Their very existence is a profound cosmic contradiction, for they have orbited our galaxy for billions of years without ever collapsing into the star-forming disk below. Their motion is the first clue that something strange is happening. They do not follow the simple, predictable orbits we would expect for mere satellites of the galaxy. Instead, they trace complex, often erratic paths, suggesting they are caught in a delicate tug-of-war with an unseen opponent, the hot, diffuse plasma of the galactic corona. This superheated atmosphere that envelops the entire Milky Way should, in theory, be shredding these clouds apart. As a cloud plows through this coronal gas at hundreds of kilometers per second, it should experience immense ram pressure, creating a bow shock at its head and stripping material away in a long, trailing tail. Our best fluid dynamics simulations predict these clouds should dissolve over mere tens of millions of years. Yet here they are, ancient and persistent, their structures often remaining coherent across eons. How do they withstand this constant, violent buffeting? The answer may lie in magnetic fields woven through the gas, acting as a cosmic skeleton that holds the cloud together, or perhaps in the invisible grip of dark matter. Some of these clouds appear far more massive than their visible gas suggests, hinting that they could be embedded within their own small, dark matter halos, whose gravity provides the necessary binding force to prevent their disintegration. The chemical fingerprints of these clouds deepen the mystery. Their metallicity, the abundance of elements heavier than hydrogen and helium, varies wildly from one cloud to another. Some clouds are almost pristine, a fossilized relic of the early universe's pure composition, suggesting they are truly extragalactic interlopers, fresh fuel falling onto the galaxy for the first time. Others show clear signs of enrichment, bearing the signature of previous generations of stars. This indicates they were likely torn from satellite galaxies or blown out of the Milky Way's own disk by past explosive events. This incredible diversity of origin stories means there is no single explanation that can account for every high-velocity cloud. They are not one population but many, each with its own unique history and fate. Their continued survival against all odds makes them critical and poorly understood components of the galactic ecosystem. They represent the ongoing process of galactic growth and recycling, a hidden river system bringing both new fuel and reclaimed material into the galaxy. Unlocking the secret of their resilience would reveal not just how gas survives in a hostile environment, but how a galaxy like our own breathes, taking in raw material from the cosmic void while managing its own complex, dynamic atmosphere. An invisible architecture weaves its way through the spiral arms of our galaxy, a force field on a scale that defies human comprehension. galactic magnetic fields stretch for tens of thousands of light-years, an unseen web that guides the flow of interstellar gas and steers the paths of high-energy cosmic rays. These fields are surprisingly weak, typically just a few millionths of the strength of Earth's own magnetic field, yet their sheer size gives them a profound influence over the entire galactic ecosystem. The leading explanation for their existence is a process called the dynamo theory. Picture the swirling, turbulent motions of ionized gas within the galactic disk as a vast, slow-moving engine. This churning plasma can stretch and twist weak magnetic field lines, amplifying them over billions of years, much like a simple bicycle dynamo generates a current from spinning motion. This elegant idea, however, confronts a fundamental chicken and egg problem. What provided the initial seed field for the dynamo to amplify in the first place? The faint magnetic fields present in the early universe seemed too weak, pointing toward a mysterious priming event that occurred long before the first galaxies ever took shape. The puzzle deepens when we compare different galaxies. Why do some spiral galaxies possess magnetic fields that are orders of magnitude stronger than our own, their fields tracing the spiral arms with breathtaking clarity, while others show only a disorganized, weak magnetism? This variation suggests that a galaxy's specific history, its rate of star formation, and the violence of its past mergers plays a decisive role in building its magnetic personality. Within a single galaxy, the field is not a uniform blanket. In the dense spiral arms and central bars, the magnetic field reveals a stunning complexity. It can twist into helical coils or suddenly reverse its direction, creating patterns that a simple, large-scale dynamo struggle to produce. These intricate structures hint at additional, poorly understood physics, where the chaos of stellar birth and death injects energy and turbulence into the system on local scales. This invisible force also engages in a powerful feedback loop with the galaxy's most energetic particles. Cosmic rays, protons and electrons accelerated to nearly the speed of light, become trapped by these magnetic fields, bouncing back and forth along the field lines. This confinement not only shapes the diffuse glow of gamma rays we see across the sky, but the cosmic rays themselves exert a pressure that can help drive colossal galactic winds, venting material and energy out into the halo. Modeling this self-sustaining cycle presents an immense computational challenge, as it requires tracking the behavior of tenuous plasma and relativistic particles across both astronomical distances and subatomic interactions. How does this system maintain its vast coherence, creating ordered structures on scales that dwarf the turbulent eddies from which they were born? The answer likely lies in a deeper understanding of magnetized plasma, a state of matter that constitutes most of the visible universe yet behaves in ways that still confound our best simulations. Unlocking the secret of these galactic fields is not just about mapping an invisible landscape. It is about deciphering one of the fundamental forces that sculpts the evolution of every galaxy in the cosmos. A star's final moments can be an act of cosmic cannibalism. Picture a sun like our own wandering too close to the immense gravity of a supermassive black hole. The tidal forces gripping the star's near side are vastly stronger than those on its far side, stretching it horizontally while compressing it vertically. This differential pull, a process called spaghettification, overcomes the star's own gravity and tears it into a stream of incandescent gas. About half of this stellar debris is flung away into the void, while the rest is captured by the black hole, forming a brief, searingly hot accretion disk. This entire cataclysm, from the initial shredding to the final glow, is a tidal disruption event, a fleeting cosmic laboratory that allows us to witness the birth of an accretion disk from scratch. The light from this event should, in theory, follow a predictable path, as the stellar material spirals inward and is consumed, the brightness should rise to a peak and then smoothly fade, following a specific mathematical decline. Yet the universe loves to defy our expectations. Observations from powerful telescopes reveal light curves that stutter and jump. Some events fade as predicted, only to experience a mysterious late-time re-brightening months or even years later. Others show dramatic shifts in the color of their light, their spectra evolving in ways that our standard models of a simple, hot disk cannot explain. These anomalies are more than just noise. They are direct evidence that the physics of how matter falls onto a black hole in these violent, single-serve meals is far more complex than we imagined. The chaos of the disruption itself, the way the gas streams collide and circularize, may create unpredictable shocks and instabilities. Perhaps the debris forms a complex, lopsided disk that precesses like a wobbling top, periodically shining its brightest light in our direction. Or maybe the black hole's own intense radiation pushes back on the infalling material, creating a feedback loop that regulates the feast. Each unexpected flicker in the data is a clue, pointing toward physical processes we are only beginning to map. The most extreme tidal disruption events do not just glow, they scream. A small fraction of these cataclysms launch relativistic jets, narrow beams of particles accelerated to nearly the speed of light. The presence of these jets appears intricately linked to the black hole's own spin and the configuration of its magnetic fields. Yet the jet launching mechanism here seems fundamentally different from the steady, powerful jets seen in active galactic nuclei that feed for millions of years. This suggests that a single, massive meal creates a unique and short-lived accretion regime, a different state of matter and energy that we can only observe during this brief window. Why do some shredded stars produce these brilliant jets while others simply form a hot disk and fade? The answer may lie in the type of star destroyed, the black hole's angle of approach, or the strength of the magnetic fields frozen into the stellar plasma as it is torn apart. Unlocking this mystery would provide a crucial bridge in our understanding, connecting the physics of these one-off events to the long-term behavior of the most powerful engines in the universe. Even the fundamental clockwork of these events holds surprises. The rate at which stellar debris falls back onto the black hole is predicted to follow a specific law, a gradual decline over time. And often it does, but frequent and significant deviations from this pattern tell us the story is incomplete. Sometimes the fallback rate is slower or faster than expected. This could mean the star was not completely torn apart, leaving a dense core to interact with the expanding debris, or it might reflect the internal structure of the star itself, as a giant star with a diffuse envelope behaves very differently from a dense, main sequence star when pulled apart. The very process of how the long, thin stream of gas circularizes into a disk may happen with an efficiency that our current simulations fail to capture. Every deviation is a message, a sign that to truly understand the violent death of a star at the hands of a black hole, we must also understand its life. The echoes of its internal structure are written in the light of its destruction, forcing us to read the story of a star's life in the brilliant flash of its end. These ghostly galaxies are defined by what we cannot see. Their starlight is spread so thin it barely registers, a faint, ethereal glow against the blackness of space. Yet when astronomers measure how these stars move, they find a profound contradiction to their fragile appearance. The outer stars of a low-surface brightness galaxy whip around at speeds that should tear these wispy structures apart, held in place only by the immense gravitational grip of an unseen force. These rotation curves provide one of the cleanest tests for dark matter, as the influence of normal matter here is almost negligible. The dark halo should be the absolute ruler of this realm, its density profile dictating the precise shape of the curve. But the universe, it seems, has other ideas. The classic prediction from cold dark matter simulations is a cuspy halo, a dense concentration of dark matter right at the galaxy's center. Yet the observed rotation curves of many low-surface brightness galaxies tell a different story. They rise gently and slowly, a signature of a soft core, a halo with a constant density at its heart. This is the persistent Core-Cusp Problem, a quiet but glaring mismatch between our most sophisticated computer models and the actual motion of stars in the dimmest galaxies we can find. The sheer dominance of dark matter here only deepens the puzzle. The mass-to-light ratios in these systems reach staggering values, meaning dark matter outweighs normal matter by factors of hundreds or even thousands. This should simplify the physics, creating a pristine laboratory where dark matter's pure gravitational influence is laid bare. Yet the relationship between the dark mass and the tiny amount of visible matter does not always follow the neat, predictable scaling laws our models expect. Why would two galaxies with the same faint luminosity, the same meager number of stars, have completely different rotation curves, one rising steeply and the other climbing at a languid pace? This divergence suggests that the total mass of the dark halo is not the only factor at play. Something else is sculpting these invisible giants. Could it be the galaxy's unique formation history, a past interaction that stirred up the dark matter and smoothed its central cusp into a soft core? Or does the answer lie with dark matter itself, perhaps a property that allows it to interact with itself, generating heat or pressure that prevents a dense concentration from forming? Each of these faint, sprawling galaxies is a unique experiment, a natural test of gravity on the largest scales. Their quiet light and unexpected motion challenge us to explain not just what dark matter is, but how it behaves when left almost entirely to its own devices, forcing a re-examination of the invisible scaffolding upon which we've built our entire cosmic landscape. This multimillion-degree plasma enveloping galaxies constitutes the majority of their normal matter, yet it remains almost entirely hidden from view. More atomic material exists in this superheated state than in all the stars, planets, and cold gas clouds combined, a fact that fundamentally reshapes our understanding of what a galaxy truly is. We are not just looking at islands of stars, but at vast, seething atmospheres of invisible fire. The primary evidence for this galactic corona comes from two distinct cosmic messengers. Sensitive X-ray telescopes can detect its faint, diffuse glow, while its silhouette appears in absorption lines against the brilliant light of distant quasars, like seeing the heat haze rising from a distant road. The temperatures and densities we measure from these observations, however, persistently refuse to align with our most sophisticated computer simulations. According to our best models, this gas should have cooled and condensed billions of years ago, raining down to fuel new generations of stars, yet it still blazes with the heat of a forgotten fury, suggesting that powerful, continuous energy sources are at work, reheating the plasma and preventing its collapse. The chemical fingerprints of this gas deepen the mystery. Its metallicity, the abundance of elements forged in stellar furnaces, varies dramatically from one galaxy to another, and even within a single galactic halo. Some regions are nearly pristine, bearing the pure composition of the early universe, hinting at fresh gas falling in from the intergalactic void for the very first time. Other areas are heavily polluted with the ashes of dead stars, clearly enriched by countless supernova explosions and the powerful outflows of galactic winds. This complex patchwork tells a story of a dynamic, chaotic ecosystem where accretion, expulsion, and turbulent mixing are constantly reshaping the galactic environment on a colossal scale. Why do some galaxies, like our own Milky Way, seem to possess a massive, extended corona, while others appear to have been stripped of this hot atmosphere entirely? The answer lies in the delicate and violent balance between two opposing cosmic forces. Accretion pulls fresh, cool gas inward to feed star formation, while feedback, the energy from those same stars and their explosive deaths, violently heats and expels gas back out into the halo. In some galaxies, this feedback may have been so extreme it blew the entire corona away, leaving behind a galactic system starved of the fuel needed for future growth. How does this seething plasma maintain its multi-million-degree temperature against the relentless drain of radiative cooling? The solution may involve a symphony of poorly understood processes, from the turbulent dissipation of energy on vast scales to the continuous injection of heat by cosmic rays and perhaps even by the dark matter itself. Unlocking the secret of the galactic corona is to understand the ultimate life cycle of a galaxy, a cycle of breathing in and breathing out on a scale that spans billions of years. There is a strange and beautiful stability to the chaos of a spiral galaxy. Grand design spirals with their sweeping, majestic arms and the central bars that cut through them are not static sculptures. They are dynamic engines, vast collective phenomena where billions of stars move in a coordinated gravitational dance that persists for billions of years. This is not the rigid motion of a spinning plate, but a flowing, self-sustaining pattern, a density wave that travels through the sea of stars like a ripple across a pond. The spiral arms we see are not permanent structures made of the same stars. They are traffic jams in the galactic flow, regions of heightened density where stars and gas slow down, pile up, and trigger the brilliant birth of new suns. The central bar acts as a great cosmic mixer, its immense gravitational field pulling gas from the outer disk and funneling it inward toward the galactic core, feeding star formation and potentially even the central supermassive black hole. Yet the very existence of this elegant structure presents a deep puzzle. Why do some galaxies develop these strong, clean bars and two-armed spirals, while others show only flocculent, patchy arms, a disorganized froth of stellar associations? The answer seems to lie in the delicate interplay of forces within the disk. A galaxy with a dominant, massive dark matter halo can suppress the formation of a strong bar, its gravity stabilizing the stellar orbits. A gas-rich disk, however, can foster the instability that gives birth to the bar, yet too much gas can also work to destroy it over time through the chaotic energy of star formation. Our most powerful N-body simulations, which model stars as simple gravitational points, consistently struggle to replicate the bars we see. They often produce bars that are too strong and too long-lived, or conversely, too weak and quickly dissolved. This persistent mismatch is a clear signal that we are missing crucial physics. The real galaxy is not just a collection of stars, it is a complex ecosystem of gas, dust, radiation, and magnetic fields. The feedback from supernova explosions and stellar winds injects tremendous energy, stirring the galactic disk and altering the gravitational potential in ways our simulations are only beginning to capture. The pattern speed of these structures adds another layer of mystery. In a differentially rotating disk, where stars at different distances orbit at different speeds, you would expect a spiral arm to wind up tightly and vanish over a few galactic rotations. The fact that they do not implies the pattern maintains a constant angular velocity, a solid body rotation that should be impossible. How can this wave, this pattern of density, remain so coherent? It must be sustained by a continuous transfer of energy and angular momentum, likely through interactions with the dark matter halo or resonant gravitational kicks from the bar itself. The longevity of these beautiful structures is a testament to a complex, self-regulating balance we are only starting to appreciate. They are not merely decorations, they are the heartbeat of a galaxy, a slow, rhythmic pulse that dictates the flow of matter and the cycle of stellar life and death across eons. These ultra-dense star cities defy our simplest cosmic categories. An ultra-compact dwarf galaxy contains the mass of a true dwarf galaxy, perhaps tens of millions of suns, but crams all that stellar firepower into a volume no larger than a globular cluster. The result is a sphere of light just a few hundred light-years across where stars are separated by mere light weeks, creating a stellar density thousands of times greater than the neighborhood around our own sun. This is not merely a crowded star cluster, it is an environment where the sheer proximity of so many suns creates a gravitational landscape unlike any other. The first great mystery is their origin. Are these the stripped and ravaged hearts of larger galaxies? Galactic archaeology suggests that some ultra-compact dwarfs do indeed contain a central supermassive black hole with a mass that is utterly disproportionate to the tiny number of stars surrounding it. This is the signature of a violent past, the ghost of a galactic core that once ruled a far larger domain, now stripped bare by repeated close encounters with even bigger galaxies. Its stars were torn away, leaving only the dense, nearly indestructible nucleus behind. Yet other ultra-compact dwarfs show no such central monster, presenting a pristine and uniform structure. This suggests a second, parallel origin story, where giant clouds of gas in the early universe collapsed directly into these incredibly dense, star-packed spheres without ever forming a more typical, sprawling galaxy. How can two such different roads lead to the same astonishing destination? The enigma deepens when we look for dark matter. In a normal dwarf galaxy, dark matter is the dominant force, the invisible glue that holds everything together. But within the crushing gravity of an ultra-compact dwarf, the role of dark matter becomes ambiguous. Some studies of stellar motions suggest these objects possess significant hidden mass, a dark matter halo that would affirm their status as true galaxies. Other meticulous observations find no evidence for it at all, with the visible stars providing all the gravity needed to explain their rapid orbits. This fundamental disagreement forces a difficult question. Are we looking at the remnant of a galaxy that had its dark matter stripped away along with its stars, or are we looking at a superstar cluster that never possessed any to begin with? Their ancient starlight holds further clues. Unlike the simple, single generation of stars found in most globular clusters, the stars in many ultra-compact dwarfs tell a complex story. Their spectra reveal multiple distinct ages and chemical compositions, evidence of several epochs of star formation stretched over billions of years. This is not the signature of a single, rapid collapse, but of a more extended and chaotic history, perhaps involving mergers between smaller clusters or late inflows of gas that sparked new waves of stellar birth. How does such a small, dense object manage to retain gas and forge new stars against the immense gravitational tides of its host galaxy? The stability of these systems is itself a marvel of gravitational engineering. With so many stars in such a small volume, close encounters and direct collisions should be common. Yet these stellar cities endure for billions of years, their populations seemingly unaffected by the internal chaos. This suggests a delicate balance, a state where the overall gravitational field is so smooth and uniform that individual stars can whip through on stable orbits without being violently ejected. Every ultra-compact dwarf is a cosmic paradox, a tiny package that challenges our definitions and forces us to reconsider how the smallest galaxies are born, live, and survive in a universe of giants. The elegant flat disk of a spiral galaxy is an illusion that shatters at its outer edges. Far from the bright core, the entire plane of stars and gas can bend upward or downward, creating a vast, slow-moving wave that travels around the galaxy. This is a galactic warp, a graceful distortion on a scale of tens of thousands of light-years. Our own Milky Way possesses one of these colossal twists, its outer disk bent like a phonograph record left in the sun. The very existence of such a structure presents a profound dynamical puzzle. According to our best models, the collective gravity of the stars themselves should act as a powerful damping force, smoothing out any warp within a few 100 million years, a mere blink in the galaxy's life. Yet we observe these warps persisting for eons, a clear sign that some continuous influence is actively forcing the disk to maintain its distorted shape. What unseen hand is perpetually twisting the galaxy? One compelling suspect is the dark matter halo itself. If this invisible shroud is not perfectly spherical, but is instead tilted or misaligned with respect to the stellar disk, its gravitational pull would constantly tug on the outer stars, forcing them into a persistent warp. Another possibility points to intergalactic magnetic fields of immense scale, exerting a subtle but continuous pressure on the tenuous gas at the galactic fringe. Or perhaps the culprit is a recent, gentle collision with a dwarf galaxy, a gravitational nudge that set the entire disk ringing like a gong, a vibration that has not yet had time to quiet. The complexity deepens when we observe the details. Some warps are simple curves, while others show a progressive twist, a wave that changes its orientation as it moves outward from the center. This intricate pattern suggests not one, but multiple sources of interference, a cosmic symphony of external forces playing upon the galactic disk. The related phenomenon of flaring adds another layer of mystery. As you move from the crowded galactic center to the sparse outer rim, the disk of gas and stars noticeably thickens. This flaring indicates that the stars in these outer regions have more energetic vertical motions, bobbing up and down through the plane like boats on a restless sea. Our models of galaxy formation struggle to explain the precise conditions needed to impart this specific kind of motion to the outermost stars. Their velocity dispersion, the random component of their speed, seems finely tuned to create this puffed-up edge, a tuning that current theories cannot fully replicate. Why would the galaxy's faintest, most isolated stars be the most dynamically excited? The answer may lie in the constant gravitational rain of small satellite galaxies and dark matter clumps, perturbations that stir the outer disk over billions of years. Together, the warp and the flare are the galaxy's memory of its interactions, a permanent record of its past encounters written in the slow, grand motions of its stars. They are a testament to a galaxy not as an isolated island, but as a dynamic entity, constantly being shaped and reshaped by the invisible architecture of its own halo and the gentle, relentless tides of intergalactic space. The periodic table is a cosmic storybook, and every galaxy writes its own version. Yet when we read these elemental histories, we find entire chapters that defy explanation. The distribution of metals, the elements forged in stellar hearts and supernova explosions, follows patterns that our best chemical models simply cannot replicate. We expect a smooth, predictable gradient from a galaxy's metal-rich center to its metal-poor outskirts, a logical outcome of the inside-out formation theory. Instead, observations reveal flattened gradients and unexpected peaks in the data, as if the galaxy's history of star formation was punctuated by sudden, violent events that thoroughly mixed the cosmic ingredients. The most profound puzzles, however, are written in the oldest stars. Scattered throughout the galactic halo are ancient suns with almost impossibly low metal content. These stellar relics are time capsules from the universe's infancy, and their chemical fingerprints are bizarrely pure. They appear to have formed from gas clouds enriched by just one or two previous supernovae, a signature that should have been erased as pristine gas mixed with enriched material over time. How did these pockets of early universe chemistry survive for billions of years without being blended into the galactic background? Our simulations of gas dynamics cannot easily create such isolated, unmixed reservoirs, suggesting our understanding of turbulence and diffusion in the early galaxy is fundamentally incomplete. Then there is the persistent case of lithium, the universe's earliest moments as described by Big Bang nucleosynthesis should have produced a specific amount of this light element. Yet when we measure lithium in the oldest stars, the abundance is consistently lower than predicted, sometimes by a factor of 2 or 3. This is the cosmological lithium problem, and it has endured for decades. Do our models of the first 3 minutes need revision, or are there unknown processes in these ancient stars that systematically destroy lithium, hiding the true primordial abundance from our view? Perhaps the answer lies in previously unimagined sites of nucleosynthesis, where rare nuclear reactions in exotic stellar environments could have altered the cosmic lithium budget. The anomalies extend to heavier elements as well. Certain elements that should be cosmic cousins, born together in the same type of stellar explosion, are sometimes found in different ratios from one galaxy to another. Why would one element be efficiently scattered through the interstellar medium while another, created in the same furnace, seems to lag behind? This points to a complex and poorly understood journey from the stellar forge to the birth of new stars, a journey involving vast galactic fountains, turbulent mixing in spiral arms, and the powerful winds from supernova remnants. Each unexpected abundance is a clue, a sign that the galaxy is not a smooth, well-mixed cauldron but a dynamic system with a memory of every explosion and merger that shaped it. To decode this elemental language is to read the full, chaotic biography of a galaxy, a story where the basic rules of chemical inheritance are still being written. A galaxy breathes in a slow, cosmic rhythm, and its breath is a fountain of fire and ice. Supernova explosions act as violent exhalations, blasting vast clouds of gas out of the star-forming disk and into the halo. This material, now far from the crowded plane, begins to cool and condense. Over millions of years, it falls back under the galaxy's immense gravity, a steady rain of cold, dense gas that will one day fuel the birth of new stars. This galactic fountain is the ultimate recycling system, a feedback loop that governs a galaxy's growth and evolution. Yet the physics of this elegant cycle is anything but simple. Within these fountain flows, gas exists in a chaotic mix of states. Cold, neutral hydrogen clouds drift alongside a seething, multimillion-degree plasma that glows in X-rays. These phases do not exist in peaceful isolation, they violently interact. The hot wind from supernova slams into the cold clouds, shredding them through a process called turbulent mixing, while thermal conduction tries to evaporate them away. Our most powerful computer simulations struggle to capture this intricate dance. The models either smooth out the details to see the big picture or focus on a small patch and miss the galaxy-wide flow. Why do some galaxies seem to operate these fountains with incredible efficiency, lifting gas high into the halo, while others show only a weak, sputtering flow? The answer seems tied to the galaxy's overall vitality, its star formation rate and total mass in ways we are still mapping. The complexity only deepens when we add invisible actors. The fountains appear to amplify the galaxy's magnetic fields, twisting them into powerful coils that can confine the falling rain. They also act as natural particle accelerators, boosting cosmic rays to nearly the speed of light. These rays then exert their own pressure, helping to push the fountain flows to greater heights and shaping their final structure. How do these delicate streams of cold gas survive their journey through such a hostile, high-energy environment? They should be torn apart, yet they persist, delivering the raw ingredients for future solar systems. Each successful rain shower is a victory against chaos, a testament to a balance of forces we are only beginning to calculate. Unlocking the secret of galactic fountains means understanding how a galaxy manages its own energy budget, a self-regulating act that determines whether it will blaze with youthful stars or fade into a quiet retirement. At the heart of these vast cosmic metropolises, the rules of physics are rewritten by sheer scale. Hundreds of galaxies swarm together, bound by a gravity so immense that it traps a seething ocean of plasma hotter than the core of any star. This is the core of a galaxy cluster, an environment where the collective behavior of thousands of island universes creates a single, unified, and deeply puzzling system. Dominating this dense center is often a single, monstrous galaxy, a brightest cluster galaxy of such extreme size and luminosity it defies simple explanation. These giants frequently harbor multiple, distinct nuclei at their hearts, dense knots of stars that appear to be the cannibalized cores of smaller galaxies. Yet their complex star formation histories, with bursts of activity occurring at unexpected times, do not neatly fit the story of a simple, hierarchical merging process. It is as if the galaxy's growth was punctuated by violent, chaotic feasts that left a scrambled record in its ancient starlight. How does such a colossal object assemble itself without the serene order our models predict? The answer is written in the hot plasma that fills the space between these galaxies. In what are called cool cores, this intracluster medium should be radiating away its tremendous heat, cooling rapidly and flowing inward in a torrent that would ignite a firestorm of new stars. Yet that firestorm never arrives. Something is actively preventing this catastrophic cooling, and the prime suspect is the supermassive black hole at the very center of the dominant galaxy. Through powerful jets and winds, this active galactic nucleus pumps vast energy back into the plasma, a feedback mechanism of breathtaking precision. But our understanding of how this energy couples to the plasma, how it heats the gas without simply blowing it all away, remains frustratingly incomplete. The feedback must be just right, a self-regulating thermostat that maintains a stable, hot atmosphere for billions of years. The invisible architecture of the cluster adds another layer of mystery. By mapping the subtle warping of background starlight, astronomers can trace the distribution of dark matter. In some clusters, this gravitational scaffolding appears oddly misaligned with the visible galaxies and hot gas, or shows unexpected clumps and substructure. This is a direct challenge to the cold dark matter model, which predicts a smoother, more predictable distribution. Are we seeing the aftermath of a recent, violent collision between entire clusters, a cosmic traffic accident still unfolding? Or does this misalignment hint at a more fundamental property of dark matter itself, perhaps a subtle interaction that allows it to lag behind the normal matter during these immense encounters? The energy in these cores manifests in even more dramatic ways. Some clusters glow with a diffuse radio light, emitting giant halos and relics that span millions of light years. These are the signatures of cosmic rays, electrons spiraling at nearly the speed of light through faint magnetic fields. The sheer scale of these accelerators is staggering, requiring a mechanism that can inject energy across the entire cluster core. The likely culprits are immense shock waves from past mergers or turbulence from the constant gravitational stirring. But how these processes efficiently accelerate particles in a plasma so thin that particles almost never collide is a problem that pushes plasma physics to its breaking point. How does a structure this vast, with components from supermassive black holes to dark matter halos, achieve such a complex and long-lived equilibrium? The galaxy cluster core is a cosmic ecosystem where gravity, plasma physics, and quantum particle behavior are intertwined on the largest scales imaginable, a natural laboratory that challenges our grasp of the universe's most fundamental laws. A galaxy can wear a ring like a crown, but one spun from cosmic conflict. Some of the most visually arresting structures in the universe are polar ring galaxies, where a brilliant hoop of gas, dust, and stars orbits at a perfect 90-degree angle to the main galactic disk. This creates a celestial gyroscope, a system spinning in two different planes at once. The most widely accepted origin story is a tale of gravitational theft. A smaller galaxy, perhaps a gas-rich dwarf, ventures too close to a larger lenticular or spiral galaxy. Instead of a full merger, the smaller galaxy is torn apart, its stars and gas captured. Over time, this captured material doesn't settle into the existing disk, but instead finds a stable orbit around the galaxy's poles, forming a pristine ring that circles the galactic waste. This should be a short-lived arrangement, however. The main galaxy's disk is not perfectly flat. Its gravitational pull is slightly uneven. This causes the polar ring to experience differential precession, meaning different parts of the ring try to wobble at different rates. According to our standard dynamical models, this should quickly twist the thin ring into a messy, puffed-up torus within just a few 100 million years. The fact that we see so many sharp, coherent rings means our understanding of galactic stability is missing a crucial component. What unseen force is keeping this cosmic hula hoop in perfect form? The answer may lie in the invisible hand of dark matter. A polar ring galaxy offers a unique laboratory because it provides two separate rotation curves. We can measure how fast stars orbit within the main disk, and then independently measure how fast gas and stars orbit within the perpendicular ring. By comparing these two maps of gravitational influence, astronomers can triangulate the true shape of the dark matter halo. The results are startling. In many cases, the halo is not a simple sphere, but is itself flattened, sometimes even aligned with the polar ring. This is a direct contradiction to the standard image of a spherical dark matter shroud, suggesting that the halo itself was shaped and twisted by the same violent event that formed the ring. Could the dark matter be interacting with itself in ways that allow it to maintain this warped configuration? The rings themselves tell different stories. Some are vibrant stellar nurseries, their blue light revealing furious ongoing star birth within the rich gas reserves. Others are composed primarily of ancient red stars, suggesting the ring formed long ago and its gas has been exhausted or stripped away. This diversity points to multiple pathways for creating these structures. Perhaps some rings are built from the slow, steady accretion of intergalactic gas, while others are indeed the remnants of a single catastrophic encounter. How can two such different processes forge the same breathtaking shape? The persistence of these perpendicular orbits challenges the very definition of a stable galaxy. They are cosmic paradoxes, beautiful contradictions that force us to reconsider how gravity sculpts matter across immense scales. Each one is a natural experiment, testing the limits of our models and revealing the hidden architecture of dark matter in a way no other galaxy can. Deep within the galactic core, a different kind of engine screams in the dark. Microquasars are stellar mass black holes or neutron stars that mimic, on a tiny scale, the colossal jets of their supermassive cousins. These systems are cosmic laboratories in fast-forward, compressing processes that take millennia in active galaxies into dramatic outbursts lasting just days or weeks. We can watch a microquasar flare to life, launch its relativistic jets, and then fade back into obscurity, all within a single observing season. This real-time view offers an unparalleled chance to dissect the fundamental physics of accretion and jet launching. Yet, these miniature powerhouses near the galactic center behave strangely. They are not simply scaled-down versions of distant quasars, nor do they act like their isolated counterparts in the galactic suburbs. Their environment, it seems, writes its own rules. The dense, turbulent soup of gas and stars in the galactic core provides a unique and rich fuel source, potentially altering how these compact objects feed and how their powerful outflows interact with the world around them. One of the most tantalizing clues from these systems is a subtle, rhythmic pulse in their high-energy light. Quasi-periodic oscillations appear as flickers in their X-ray emissions, a rapid, almost musical beat underlying the chaotic roar. These frequencies may be the fundamental vibrations of the accretion disk itself, the sound of matter spiraling inward at the very brink of the event horizon. One model suggests the inner edge of the disk is oscillating, ringing like a struck gong. Another proposes the entire jet is precessing, wobbling like a top and sweeping its beam across our line of sight. Or perhaps we are hearing the precise orbital clockwork of material trapped at a specific resonance around the black hole. The debate over the exact mechanism continues because each of these ideas makes different predictions about how the frequency should change with the system's brightness and evolution. When these microquasars do erupt, their jets slam into the dense interstellar medium of the galactic center with incredible force. Unlike the jets from isolated systems that travel through relatively empty space, these create massive, expanding radio lobes and complex shock structures. We see these interactions light up, providing a visible map of how a hypersonic beam of plasma plows through a molecular cloud. It is a natural experiment in high-energy hydrodynamics, showing us how energy and momentum are transferred on a colossal scale. Why would a stellar mass black hole in the crowded core act so differently from one born in the galactic emptiness? The answer may lie in the pressure and the fuel. The constant gravitational tides and the sheer density of available gas could stabilize the accretion disk in one system while destabilizing it in another, or it could influence the strength and configuration of the magnetic fields that ultimately launch the jets. Understanding microquasars is not just about studying these individual systems. It is about discovering the universal principles that govern how all black holes, from a few solar masses to billions, feed, grow, and interact with their cosmic environment. Galaxies in the universe's first chapters should be fragile, chaotic things, mere infants taking their first gravitational breaths. Yet the James Webb Space Telescope is showing us a different story entirely, a cosmic narrative where maturity arrives impossibly fast. We are seeing fully formed, massive galaxies at distances so vast their light has traveled for over 13 billion years to reach us, galaxies that by all rights should not exist in such a developed state. Their starlight tells us they contain vast populations of old suns and hold a surprising abundance of heavy elements, the metal forged in earlier stellar generations. This presents a profound timeline problem. Our standard models of galaxy formation simply do not allow for such rapid cooking. How could stars form so efficiently, live their lives, explode, and enrich the galactic gas, all within the first few 100 million years after the Big Bang? The very clockwork of cosmic evolution appears to be running fast, forcing us to reconsider the fundamental rules of how a galaxy is built. Perhaps the first stars formed with a different distribution of sizes, leaning more toward massive giants that lived fast and died young, seeding the cosmos with metals in a furious rush. Or maybe the dark matter halos that cradle these early galaxies assembled with a shocking speed and density, creating deeper gravitational wells that pulled in gas and ignited star birth with an efficiency we see nowhere else in the later universe. The most startling anomalies are not just massive, they are orderly. Some of these ancient galaxies show the clear, rotating structure of a disk, a pinwheel spinning in the primordial dark. This is a direct challenge to our picture of the early cosmos, which was dominated by violent mergers and chaotic gas collisions. A stable disk requires a serene and settled existence, a period of quiet growth that theorists thought was impossible so soon after the universe began. Their existence suggests that some galaxies found a path to maturity that bypassed the era of chaos entirely, assembling with a grace and speed we never anticipated. This accelerated timeline creates a parallel crisis for the supermassive black holes we find lurking in these early galaxies. To reach billions of solar masses so quickly, these black holes would have needed to start from immense seeds, far larger than the stellar mass black holes we see forming today. Or they would have had to feed at a rate that pushes against the ultimate theoretical limit, the Eddington limit, for hundreds of millions of years without pause. How does a black hole consume matter so relentlessly without blowing away the very gas that feeds it? Each of these cosmic prodigies is a data point that strains our models to the breaking point. They are not just oddities, they are evidence. They suggest that the conditions in the early universe were not just a simpler version of what we see today, but a different physical realm altogether, operating under a set of rules we are only beginning to glimpse. Do these high-redshift anomalies point toward new physics in galaxy formation? Or could they even hint at a need to revise our most fundamental cosmological parameters, the very numbers that describe the expansion and content of the universe itself? Every distant point of light is a question, challenging the story we thought we knew about how everything began. A single magnetic pole wandering through the void would rewrite physics from the ground up. These hypothetical particles, known as magnetic monopoles, are the universe's missing pieces, the isolated north and south poles that should exist if our theories are correct. The equations of grand unification, which attempt to weave together the electromagnetic, weak, and strong nuclear forces, almost demand that these entities were forged in the unimaginable heat of the universe's first moments. During the rapid cooling and phase transitions of the early cosmos, these fundamental magnetic charges should have been frozen into the fabric of reality like cosmic fossils. Yet despite this powerful theoretical prediction and decades of dedicated searching from deep underground laboratories to instruments in space, the universe has offered us only silence. Not one confirmed monopole has ever been found. This profound absence is the monopole problem, a quiet crisis that suggests our most ambitious theories of cosmic unity might be incomplete, or that we are missing a crucial chapter in the story of the universe's infancy. Where did all the monopoles go? Their sheer theoretical weight makes their non-detection one of physics' most stubborn puzzles. Some ideas propose that cosmic inflation, a period of fantastically rapid expansion, diluted their numbers to near zero, scattering them so thinly across the cosmos that finding one becomes a monumental task. Others suggest they are hiding in plain sight, clustered within the cores of stars or planets, or perhaps even constituting a portion of the universe's mysterious dark matter. The potential influence of a monopole is as strange as its elusiveness. According to certain theories, a monopole could act as a catalytic site for proton decay. In the Rubikov-Kalin effect, a proton encountering this exotic particle could unravel, its fundamental stability overcome in an instant. This process could potentially explain anomalous high-energy events in our cosmic ray data, offering a faint signature of a particle we cannot see directly. Their journey through a galaxy would be unlike any other. A magnetic monopole would not simply drift, it would be continuously accelerated by the galaxy's own magnetic fields, surfing on lines of force in a way no electrically charged particle ever could. This unique motion might leave a distinctive imprint in the highest energy cosmic ray spectra, a subtle bump in the data that has so far escaped definitive identification. The very existence of the large-scale magnetic fields we see woven through galaxies could even be a clue, perhaps generated or amplified by a primordial sea of these particles. How do we find something that has evaded every trap set for it? The continued silence forces us to consider ever more creative methods of detection and increasingly refined theoretical models. The mystery of the magnetic monopole is a profound reminder that the universe may be equipped with fundamental building blocks we have not yet learned to see, and that the answers to our biggest questions might be waiting in the quietest corners of the cosmos. A galaxy floating in a cosmic desert faces a very different set of rules. These are the void galaxies, isolated islands adrift in the largest and emptiest structures in the universe. Regions spanning hundreds of millions of light-years where the density of matter can be less than 1/10 of the cosmic average. To be born here is to grow up in profound solitude, cut off from the gravitational tides and galactic collisions that shape the crowded urban centers of the cosmos. The few galaxies that do form in these immense voids are cosmic hermits, and their quiet lives tell a story that challenges our most fundamental ideas about galactic evolution. These isolated systems often possess a primal purity, their starlight revealing a lower abundance of heavy elements, a sign that they have been largely untouched by the metal-enriching winds from neighboring galaxies. They tend to be gas-rich, holding onto the primordial hydrogen fuel that more social galaxies quickly burn through or have stripped away. Many are irregular in shape, frozen in an adolescent state, as if the lack of external pressure has allowed them to avoid growing into the mature spirals and ellipticals we see elsewhere. Why would a galaxy's fate be so deeply written by the emptiness that surrounds it? Our standard models of galaxy formation, which rely on environment-independent recipes, consistently fail to reproduce the precise properties of these void dwellers. They predict different mixes of galaxy types, different rates at which gas turns into stars, and different histories for the dark matter halos that cradle these lonely stars. The very existence of these galaxies and their unique characteristics suggests that the environment is not just a backdrop, it is an active participant in a galaxy's life from the very beginning. Some of the voids themselves hold deeper mysteries. Certain vast, empty regions of sky show unexpected cold spots in the cosmic microwave background, the faint afterglow of the Big Bang. While some of these could be statistical flukes, others may be imprints of the void's immense underdensity itself, or perhaps even signs of previously unknown large-scale structures or physical processes that only manifest in these extreme low-density environments. How does a galaxy assemble itself when it has almost nothing to build upon? The answer forces us to reconsider the delicate balance of gas accretion, star formation, and feedback in near-total isolation. These cosmic hermits are not failed galaxies, they are natural experiments demonstrating what happens when a galaxy is left to its own devices, free from the constant jostling of the cosmic crowd. Their quiet, unassuming light provides a critical test for our models, pushing us to write a more complete story of galactic life, one that accounts for the profound influence of nothingness. For nearly 2 decades, a stubborn and brilliant mystery has pulsed at the very heart of our galaxy. This is the galactic center gamma-ray excess, a persistent and unexplained glow of high-energy photons concentrated around the core of the Milky Way. It is not the uniform background we would expect from known processes, nor does it perfectly match the expected light from pulsars or cosmic ray interactions. Instead, this signal forms a distinct, spatially extended component that peaks at an energy of 2 to 3 giga-electron-volts, creating a unique fingerprint in the cosmos. The very shape of this emission is the first major clue. Its morphology roughly follows the distribution we would predict for a halo of dark matter, a tantalizing hint that we might be witnessing the invisible majority of matter finally announcing its presence. Yet the match is not perfect. Subtle differences in how the glow is distributed complicate a simple dark matter story, leaving astronomers to wonder if they are seeing the ghostly signature of a new particle or something else entirely. The leading astrophysical explanation points to a vast, unseen population of ancient stellar corpses, millisecond pulsars, the rapidly spinning remnants of dead stars, could collectively create a diffuse gamma-ray glow. However, these faint objects struggle to reproduce the exact spectral shape and smooth spatial distribution of the excess. Recent discoveries have added fascinating new layers to this puzzle. Sensitive telescopes have begun to resolve some of this glow into faint, individual point sources, suggesting that at least a portion of the signal does indeed come from a previously hidden population of pulsars. Yet, even with these discoveries, the overall mystery endures, as the combined light of these newfound objects does not fully account for the signal's pervasive intensity and unique characteristics. The plot thickens when we look at the galactic center in different forms of light. This gamma-ray excess appears to have cousins. There is a corresponding, unexplained glow in X-rays and a vast bubble-like structure known as the microwave haze. Are these different signals all connected, tracing a single, colossal event or a fundamental new process? Or are we seeing the complex interplay of radiation fields in the galaxy's most crowded and chaotic district, a place our models of interstellar physics are not yet sophisticated enough to fully map? Time itself has become a critical tool in this investigation. If the signal were from dark matter annihilation, it would be perfectly steady, unchanging over human timescales. If it comes from a population of pulsars, it might flicker in ways we could eventually detect. So far, the signal has remained stubbornly constant, placing constraints on some of the more exotic interpretations, but failing to provide a definitive answer. After nearly 20 years of observation and debate, the fundamental nature of this excess remains one of astrophysics' most compelling open cases. What physical process, either a new class of astronomical object or a particle physics phenomenon beyond the standard model, is capable of generating this persistent, high-energy hum? Solving this mystery will require more than just a bigger telescope. It demands a leap in our understanding of what is possible in the universe's most extreme environments. These galactic puzzles force us to question the bedrock of physics, the very nature of gravity itself. For decades, the dominant solution to every cosmic anomaly has been dark matter, an invisible substance that outweighs normal matter 5 to 1. But what if the answer is not a missing ingredient, but a flaw in the recipe? A bold alternative suggests that our understanding of gravity, a force we thought was settled by Newton and Einstein, might be incomplete in the vast, sparse outskirts of galaxies. This idea, known as modified Newtonian dynamics or MUND, proposes that gravity behaves differently at extremely low accelerations, the kind experienced by stars drifting in a galaxy's faint outer halo. In this framework, the need for dark matter vanishes, replaced by a subtle adjustment to the laws of motion. For some individual galaxies, especially those low-surface brightness ghosts, man can predict their rotation curves with striking accuracy, a success that keeps the theory alive and compelling. Yet this elegant solution struggles to explain the bigger cosmic picture. When we zoom out to the scale of massive galaxy clusters, the observed gravitational pull, especially from the seething hot plasma between galaxies, still demands some form of unseen mass that man cannot easily account for. The intricate patterns of the cosmic microwave background, the ancient light from the Big Bang, also fit perfectly within the dark matter model, but present a serious challenge to modified gravity. The theoretical landscape has expanded with even more complex proposals, from tensor vector scalar theories that add new fields to spacetime, to ideas where gravity emerges from the quantum information of fundamental particles. Each framework attempts to solve a specific set of puzzles, whether the precise motions of stars or the lensing of light, but each also introduces its own new complications, often failing in other extreme environments where dark matter succeeds. Perhaps the most profound connection lies between these galactic-scale mysteries and the ultimate cosmic unknown, dark energy. This mysterious force driving the universe's accelerated expansion is typically treated as a separate problem from the behavior of individual galaxies. But what if the two are linked? Could the same fundamental misunderstanding of gravity that creates the illusion of dark matter on galactic scales also be responsible for the apparent effect of dark energy on the cosmos as a whole? Some theories propose that the vacuum energy of space itself, or a new, long-range force, might simultaneously explain why stars orbit too quickly in galaxies and why the universe is flying apart. The true nature of gravity is being tested in these extreme environments, and the final theory, the one that ultimately prevails, must be a universal one. It must account for the precise orbit of a single star around a black hole, the grand rotation of an entire galaxy, the violent collisions of galaxy clusters, and the relentless expansion of the entire cosmos, all within a single, coherent mathematical framework. We are left with a universe that provides the questions but stubbornly withholds the answers, forcing us to look ever deeper into the darkness. Our journey through 30 cosmic frontiers has revealed a universe where reality constantly defies our expectations. From the silent, crushing heart of a neutron star to the invisible architecture of dark matter halos, we have stood at the very edge of known physics. Each extreme environment, from the brilliant fury of quasars to the ghostly silence of dark galaxies, presents a unique challenge to our fundamental theories. These are not failures of our models, but signposts pointing toward a deeper truth we have yet to grasp. The subtle anomalies in galactic rotation, the mysterious timing of stellar disruptions, and the persistent, unexplained glows at our galaxy's core all whisper the same message. Our current understanding is a magnificent but incomplete map, and the most exciting territories still lie blank, marked only by the words "Here be dragons." The coming era of discovery promises to fill in some of those blanks. Powerful new instruments like the James Webb Space Telescope and the upcoming Vera-C. Rubin Observatory are already peering deeper into the cosmic dawn, while gravitational wave detectors listen for the faint ripples of unseen collisions. Advanced particle detectors buried deep underground continue their quiet vigil, hoping for a glimpse of the universe's most elusive constituents. With every new observation and every sophisticated computer simulation, we refine our questions and sharpen our search. Yet for every mystery we solve, the cosmos seems to unveil two more, each one more bewildering than the last. This endless cycle of discovery is the very engine of science, a perpetual reminder that the universe is far stranger and more wonderful than any fiction. The true value of these cosmic puzzles lies not in the answers we might one day find, but in the journey of questioning itself. They invite us to look up at the night sky with fresh eyes, to see not just points of light, but the brilliant, violent, and mysterious processes that shape our galactic home. Which of these extreme environments captures your imagination the most? Share your thoughts on the cosmic frontiers that you find most compelling.